Hello, and we're back to AP Physics. Topic of today is conservation of momentum. Just as before, it doesn't mean like save it. Conservation of energy meant that however much energy we started with was the amount of energy that we ended up with. That's going to be the same thing with momentum. However much momentum we started with is going to be the amount of momentum that we end with, assuming there's no outside forces that are coming into play. So if we have a cannon and a cannonball, okay, which of these is going to change momentum after firing? Which one of these, initially they're stationary, which one of these is going to move? Well, theoretically, they're both going to kick back a little bit. The ball is going to go forward and the cannon is going to have recoil. It's going to kick back. So Newton's third law, okay, which one of these felt the greater force? The cannon and the ball are same. Okay, is the same. They feel the same force. Which one of these has the force on it for the longest amount of time? Cannon, ball, or same? Well, that's certainly going to be the same. They're going to feel the force for the same time. So they're both going to experience the same force, okay, at least magnitude, for the same time, which means they're going to have the same impulse. Okay? And since they have the same impulse, that means they're both going to experience the same change in what? Velocity, speed, and momentum. Well, I hope you said momentum, because if you did, you are correct. Okay, they're going to experience the same change in momentum. So they both start with zero momentum. They're both going to change by the same amount of momentum. So afterwards, which of these is going to have the most momentum, the cannon or the ball, or same? Okay, well, if they start with the same, which is zero, and they both change by the same amount, which is some number, okay, they're both going to end up with the same amount. Okay, so they're going to end up with the same amount of momentum, but what's going to be different about the momentum, okay, is that the cannon had the large mass and a small velocity. Okay, in order to have the same amount of momentum, the cannonball with the small mass had a large velocity. Okay, so that's one thing that's different about the momentum of the two. The other is that they both had the same amount of momentum, but it was in different directions. So how are we going to represent the different directions of the momentum? We're going to use different signs. Okay. So let's say that they initially started with zero momentum. Afterwards, the cannon ended up with plus 5 kilogram-meters per second units of momentum, and the cannon itself ended up with negative, because it's going backwards or to the left, 5 units of momentum. So what am I going to get if I add these up? Okay, I'm going to get 0. Okay, so the initial momentum of the cannon and the ball system, okay, my objects of interest, was 0 because nothing was moving. Okay, afterwards, okay, when I add up the momentum of the cannon and the ball, I get 0. That's what we mean by the total amount of momentum is conserved. However much momentum I start with, 0, is equal to the amount of momentum that I end up with, 0. Okay, and it doesn't have to start with 0. It can start with, you know, 1,000,000 units of momentum. But the thing is, as long as there's no outside forces, the momentum is going to remain constant. Okay, so and I've mentioned this a couple times. Let me just here it is in writing. Without an external force, as long as there's not an external force, the momentum of the system doesn't change. That's what conservation of momentum means. An external means something besides the things we're looking at. Okay, a system means the things that we're looking at. So we're looking at the cannon and the ball. That's my system. Anything outside or anything other than a cannon or ball, if it contacts my system or exerts a force on my system, that is an external force. Okay, my little box is drawn around my cannon and the ball. That's the only thing I'm looking at. So anything other than that is external. Okay, so if I had a large truck that came along and ran into my cannonball system, that would be an external force. Okay, what about friction? Would friction be an external force, external to my system? Sure, it would be, because it's friction between the earth and the cannon, and the earth is not part of my system, so that would be considered an external force. Okay, so some review questions here. We have a meteorite, okay, and it slams into the earth and sticks. Okay, during the impact, which has the greater force on it, the meteorite or the earth, or same? Okay? It'd be the same force. Which has the greater momentum? Okay, or I'm sorry, which has the greater impulse? Which has the greater impulse on it? It'd be the same because they experience the same force for the same time. Which is going to change momentum more? Okay, the meteor or the Earth? Well, since they have the same impulse, they're going to have the same change in momentum. That doesn't mean they end up with the same momentum. It means that it's going to change by the same amount. Okay. What happened to the momentum of the Earth meteor system? Well, okay, as long as there was no outside forces, okay, the momentum of my Earth meteor system is constant. Okay, which one feels the greater acceleration, the Earth or the meteor, or same? Okay, that would be the meteor. The meteor, even though they have the same force on them, the meteor is going to have has less mass, so that force is going to affect its motion much more pronounced. Okay, so throwing some numbers at conservation of momentum, what we're going to say is, however much momentum I start with, okay, I'm going to look at each individual part. Usually I'm going to have two parts. Will be kind of the systems that we deal with. The initial momentum of part 1 and the initial momentum of part 2, okay, is going to equal the final momentum when I add up the momenta of part 1 and part 2 over here. Okay, so the sum of my initial momentum is going to equal the sum of my final momentum. Okay, 0 equals 0 if we start with 0. Okay, so for a two-part system, we got object A and object B. This is not an equation you need to write down or anything like that. This is just another way of saying initial equals final. So the initial momentum of object A plus the initial momentum of object B equals the final momentum of object A plus the final momentum of object B. So that's not one that I would write down. Let's work a problem with this. So here we've got Jack and Jill. They're wearing roller skates. Okay, so they're frictionless roller skates apparently too. They're initially at rest. Okay, and they're right next to each other. They push off of each other. And afterwards, Jack is moving with a velocity of 10 meters per second to the right. And we're wondering what Jill's velocity is. Okay, so this is a situation where initially they're at rest, so my initial momentum is 0. So this is like our cannonball system. Okay, so the initial momentum of Jill is 0, and the initial momentum of Jack is 0. So that's 0 on this side, P Jill plus P Jack. Okay, now that's going to equal the momentum on the other side. So we know Jill's mass is 40 kilos, but we don't know her velocity, so we're just going to leave that as v, and hopefully that's our only unknown. And then we know Jack's momentum after they push off is 10 meters per second, and he's got a mass of 80 kilograms. So 80 times 10 is his momentum. So now we've got an equation. All we do is solve it. And when we do that, we get that the velocity of Jill is equal to negative 20 meters per second. Okay, what is the significance of the negative? And of course, it's that she's moving to the left. So if Jack has positive momentum, Jill's going to have negative momentum in order for that to add up to be 0, like it is on the other side. Okay. Let's work another problem. We've got a 10 kilogram car moving to the right at 3 meters per second, hits a 20 kilogram car moving to the left at 5 meters per second. Okay, after the collision, car A is moving to the left at 1.5 meters per second. What is the velocity of car B, or what is of the 20 kilogram car? Okay. I think it's usually pretty helpful to draw a picture, before and after picture. That kind of helps me keep these things organized, because there's a lot of numbers that you got to keep the right number with the right numbers. So we've got our 10 kilograms moving at 3 to the right. So that's initial, and our 5 and we also have our 20 moving at 5 to the left. So we've got 3 times 10 on the initial side, plus negative 5 times 20. Okay, we got to make sure that we watch directions and signs here, because that left is key. We'd be completely wrong if we left that off. So that's our initial side. On our final side, we know that car A, the 10 kilogram car, is moving at 1.5 meters per second to the left. So again, we've got our negative to denote that it's to the left. Okay, plus the velocity, however fast car B is moving, times its mass. Okay, so that my initial momentum equals my final momentum. And again, we're setting that equal. So when we solve, we get that the velocity of car B is negative 2.75 meters per second. So 2.75 meters per second to the left. Okay, so I started with negative momentum and I'm going to end with negative momentum. Okay, initial equals final. Okay. Did I load this new applet? So this is a Newton's cradle, which is an example of conservation of momentum. So let's say we drop one of these, there's a collision, and then that momentum is transferred to the other side. Okay, and that momentum keeps getting transferred back and forth and back and forth and back and forth. So let's start with two of these, and we'll have twice the initial momentum. Okay, and then afterwards we'll have twice the final momentum. Okay, I think it's cool how that middle one just doesn't move. Okay, now we can do 3, and that the middle one just keeps on going. Whoops, there we go. Just keeps on going, and the other 2 stop. And then we can do 4. But the best is 5. Yeah, I know, that's amazing, isn't it? Woohoo! So again, this is an example of conservation momentum in a collision. So where's my point? There we are. I had a really good video link of a guy holding a rifle in a manner which is really not appropriate for like lacking pain. He didn't put the butt of it against his shoulder. He held it with like outright with 2 hands and right in front of his face, and then he fired. And then conservation momentum tells us when the bullet moves to the right, okay, the gun or cannon, as we were using an example of cannon, cannon's going to move to the left, and it just smashes into the guy's face. And I can't find it, which is unfortunate, but whatever. Okay, so what we saw was that when two of the balls smashed into the other one, 2 came out the other side. Okay, because we had twice as much momentum as one ball. Okay, but why couldn't we get, instead of having 2 come out, why couldn't we have 1 come out with twice the speed? Wouldn't that satisfy conservation of momentum? Okay, so here we've got two in and 2 out. Okay, conservation momentum. My initial momentum was I made my spheres 1 kilogram each to make the math easy. So our initial momentum was 2 kilograms times 3 meters per second, 6 kilogram meters per second. And my final momentum was that. Okay. Now, what we haven't talked about with this yet is energy, how energy comes into play, because energy must be conserved too, in what's called an elastic collision, and these are elastic collisions. So my initial kinetic energy is 2 kilograms, because I've got 1 kilograms, times 3 meters per second. They're both moving at 3. Okay, that gives me 9 joules. And my final kinetic energy was going to equal 9 joules because it's basically the same thing. Okay, so that's if we have 2 come in and 2 pop out at the same velocity, momentum is conserved and energy is conserved, and everybody's happy. Okay, let's look at what happens if 2 come in and 1 comes out at twice the speed. Okay, so the momentum, we'd have 1 kilogram, and instead of moving at 3 meters per second, it's going to be moving at twice the speed. It's going to be moving at 6. So I get 6 units of momentum. So I'm starting with 6 units of momentum, and I'm ending with 6 units of momentum. Okay, how do you think energy is going to play out? Why doesn't this happen? Okay. Well, now if we plug in the 1 kilogram and the velocity of 6 meters per second, we get 18 joules. So that would violate conservation of energy because we would have twice the energy coming out as the collision as we had going into it, and that would not work without some other energy supplying device. So anyway, that's why that does not happen. So we've been looking at collisions. We've been looking at situations where the momentum add up to zero, like explosions, but there are a lot of times when the initial momentum won't be zero. In an explosion, the momentum is zero, but a lot of times the momentum will not be zero, because in order for things to hit each other, something has to be moving. So most of the time, or a lot of times in collisions, the initial momentum is going to be some value. And there's two main types of collisions. There's elastic collisions and inelastic collisions. And I would make a mental note of this. In inelastic collision, objects hit, they bounce, and there's no energy lost. Okay, no energy is lost in an elastic collision. Okay, in an inelastic collision, okay, objects hit and they stick together. Okay, energy is lost. So elastic bounce, no energy lost. Inelastic stick, energy is lost. Okay. But no matter what in these, momentum is always conserved, assuming there's no external forces. Okay. So so let's look at some collisions. So let me see if I. Oh, bummer. So I'm going to put a link to this applet so you guys can play around with this a little bit if you want. But these are our carts, and you can generate various collisions, and you can see what happens. So here we've got, let's make both cars of equal mass, and then we'll run one car into the other one. So here's my car with 5 units of energy, and it's going to collide elastically into this car. And basically, the energy from the red car, the momentum, well, momentum and energy, the momentum from the red car just got transferred into the blue car, and it moved off at the same speed. So I can, and because they had the same mass, if I start with the red car heavier, okay, now I've got 10 units of momentum, and it's going to give some of that momentum to the blue car, and it's going to keep some of its momentum. But notice the total amount of momentum is going to add up to be is going to still add up to be 10 units of momentum, or at least it should. Okay, was it 5 meters per second times 2 kilograms? Yeah, it should. Yeah. Okay. Now I can do this the reverse way. I can have the other car heavier. Okay, and we're starting out with 5 units of momentum now. Okay, and we'll bump into the other car, and now this time this car bounces back. So we've got some positive momentum over here, and then we've got some negative momentum over here. So that would still have to add up to be my positive momentum that I started out with. And so those are. Let me put it back to the same reset. Okay, now that was those were elastic collisions. If I switch this to inelastic collisions, okay, then we're going to start with 5 units of momentum, and then afterwards we're going to end up with 5 units of momentum. So here we've got a 2 kilogram car moving off at 2.5 meters per second. So we've got so that gives us our 5 units of momentum. So again, they hit and stick on an inelastic collision. They hit and stick. So you can play around with that applet at your leisure. Let's see. So let's work a problem here. There's just a couple more things I want to get through, and then we'll be done. It's going to be a little bit of a longer note, probably 26 minutes, somewhere in there. Okay, so here we've got a 6 kilogram car moving at 12 meters per second hits an 18 kilogram car at rest. Okay, what is the velocity if they hit and stick together, if it's an inelastic collision? So let's do that. So draw a little picture. So here's my 6 kilogram car moving at 12 meters per second. Here's my 18 kilogram car at 0 meters per second. So we're starting out with 6 times 12, 72 units of momentum. So I'm going to have 72 units of momentum after the collision. Okay, so after they collide, now the 6 and 18 kilogram object, they're stuck together, so we're going to consider them a 24 kilogram object. Okay, that's the trick to this, is just consider them one object and add up the masses. And so we get that our velocity is 3 meters per second. Another way we can look at this is that the mass went up by a factor of 4, went from 6 to 24 units. And my velocity went down by a factor of 4, went from 12 to 3. So if you like to play numbers in your head, then you can do games like that. What about the kinetic energy? Well, my initial kinetic energy was 6 times 12 squared over 2. That's my mass times velocity squared. It was 432 joules. Okay. Afterwards, my 24 kilogram object was only moving at 3 meters per second. And we get 108 joules. So that means we lost 321 joules in our inelastic collision. In inelastic collisions, energy is lost. And in the real world, collisions are always a certain percentage inelastic. We never have perfectly elastic collisions, unless we're talking about atoms bouncing around, and the collisions between atoms is perfectly elastic. So again, just to try to reiterate these a little bit. In elastic, objects bounce, energy is conserved, and momentum is conserved. Okay. In inelastic, objects hit and stick together, energy is lost. Okay? Energy is not conserved, but momentum is still conserved. Momentum is always conserved in any collision, assuming there's no external force. So you can always use conservation of momentum. Okay, so we talked about different scenarios when energy is conserved and when it's not. That gets to be kind of a big deal with how you approach a problem. But generally there's going to be clues in the problem. Sometimes they'll be extremely obvious. Sometimes they'll be a little more hinted at, I guess. In the absence of friction, obviously, is they're telling you energy is conserved. Two things collide and stick together, that's telling you energy is not conserved because it's an inelastic. Cars collide and bounce elastically, that's telling you energy is conserved. Okay, how much energy is lost? It's probably telling you that energy is not conserved, or given that energy is conserved. Okay, so there'll be clues, things like that. So the last thing I want to cover is what's called a ballistics pendulum, and this is a good example of energy and momentum in action. So basically, I don't really know the history of this, but I'm pretty sure these were used to determine the exit velocity of bullets before more modern ways came about. And what they would do is they would fire a bullet into this catcher, which is on a pivot, okay, and then the pivot would catch the bullet, and then they would rise, and it would reach a point, and then it would lock and stop, and they would look at how much the pendulum rose, and they would calculate the velocity of the bullet. So kind of interesting old school method of doing this before more modern versions with high-speed cameras and whatever were used. They may still use these, I don't know. I doubt it, but maybe. Okay? So this is what a problem would look like, an example problem. So we've got a bullet of certain mass traveling at a certain speed, and it's going to embed itself, or it's going to be caught into a block of known mass. And then I might ask you how high the block rises. Okay, or I could ask you the opposite, and I could give you the masses and how high it rises, and then ask you to calculate the velocity of the bullet, which is what they would have done. So, you know, it's 6 and 1. It's just working the problem forwards or backwards. It doesn't really matter. You do approach it basically the same way, just one way versus the other. Okay. So let's see. So my bullet enters and embeds into this block, and it rises. Okay, and it starts to rise. So is energy going to be conserved in this scenario? Yes or no? Well, let's take a look at what we just learned. What type of collision is this between the bullet and the block? Is that an elastic or inelastic? Okay. If you said inelastic, you are correct. So will energy be conserved during that collision? No. Okay, so energy will not be conserved during the collision of the block, but it will be conserved while the block and the bullet are rising up on these pendulum swing. Okay, so basically we're going to look at this at 3 different points. 1, the bullet's approaching the block. 2, the bullet has embedded in the block and has just barely started to move. Okay, and number 3, the block and the bullet have swung up to their maximum height. So those are the 3 points that we're going to look at. Okay, and let's figure out how high this thing is going to rise. So the first thing we're going to do is we're going to treat this as an inelastic collision. So we've got 3 grams. Now that of course needs to be in kilograms, so 0.003. Okay, so we're going to do conservation of momentum first, or not energy, of momentum. So mass times velocity, or velocity times mass, doesn't matter the order. Okay, so that's my 0.003 times 850, plus the momentum of the block, which is 0 because it's at rest. Okay, then we're gonna look at the 2 objects together, so 1.003, and we want to figure out the velocity that they're going to move off together with. Okay, so solving that, we get that the velocity of the block bullet system is 2.54 meters per second. So that's how fast they're moving after the collision has occurred and the bullet has shared its momentum with the block. Okay. Next, we're going to treat the bullet and the block as one object traveling at 2.54 meters per second. And we're going to use conservation of energy to try to figure out how fast or how high that thing is going to rise. So we'll say my initial potential plus my initial kinetic equals my final potential plus my final kinetic. There's no springs or anything, so we're only talking gravitational potential. Okay, so here this is my initial situation, okay, or this one down here, and that's my final situation. So my initial potential is 0 because I'm at my lowest point, so we're going to consider that to be 0. We do have kinetic energy given by the mass times the 2.54 that we just found out, squared over 2. Okay, and that's going to equal, okay, the final potential, which is however high it goes, okay, plus the final kinetic, which is going to be 0 because it's going to come to a stop at the top. Okay, so and my gravitational potential is mass times gravity times height. The mass cancels out, and we get that the height, it's going to rise and be 0.329 meters. And so I could give you the meters, and I could say what was the velocity of the bullet and that sort of thing. And that is it for today. Sorry about having a little bit longer than normal, but it is what it is, right?